All right, well, it's 12 o'clock, so we can go ahead and get started. Hi, everyone. I want to welcome you all to the Montana Institute on Ecosystems Rough Cut Seminar Series. I'm Paige Tollison, and I'm the program manager at the IOE. Next week, we will be hearing from Dr. Arthur Middleton, who is an associate professor of wildlife management and policy at UC Berkeley. Arthur will be speaking on an inflection point in the conservation of wide-ranging wildlife across the greater Yellowstone ecosystem. And as a reminder, this seminar is being recorded, and we ask that you turn your cameras and microphones off during the presentation. And please save your questions for the end of the talk, but feel free to type questions in the chat as the talk goes on. And I'll hand it over to you, Andy, to introduce our speaker.
Hey, thanks, Paige. Yeah, Andy Hansen. I'm the new director of the Institute on Ecosystems here at MSU. I think, as you know, this semester the Rough Cuts has been exploring the greater Yellowstone ecosystem, including global change drivers, responses of species and ecosystems, and implications for policy and conservation planning. So we're particularly pleased to welcome Steve Hostetler to talk to us today about climate variability, which of course is in fact one of those major global drivers that is so much a force in influencing nature and people across our ecosystem. Steve is a research hydrologist, recently retired from the U.S. Geological Survey, Northern Rocky Mountain Science Center. His research focuses on developing and applying global and regional climate models, also surface process models, and uses both to try to explain interactions between atmosphere and aquatic and terrestrial systems, including concerns about land use change, wildfire. Among his many applications of these approaches was a recently completed Greater Yellowstone Climate Assessment, which you hopefully have seen, and which of course has already become a really invaluable contribution to our community. Today, Steve is going to talk to us about, as you can see here, ongoing and future climate change and GYE. Steve, we really look forward to your talk. Thanks for joining us.
Oh, thank you, Andy. And thank you all for joining the talk. I appreciate you taking the time. What I'm going to talk about today is, since it's rough cut, I put some things together that are related and of some interest, I think, both in the recent past and maybe looking toward the future. I'm going to talk a little bit about observed climate changes, and then I've been doing some research on Holocene atmospheric rivers using our regional climate model. So I went ahead and modeled the event in June, and so I'm going to give you some insight into that from our models, and then finish off with some changes in how rain and snow and rain on snow that cause which are another cause of these events might look in the future. So this is a pretty familiar slide here. We're looking at the CO2, observed CO2 since 1960. And along with that, the rise in both global temperatures over land and over oceans. We've all seen this, I think, plenty of times. We know what's going on. The oceans are warming at roughly half the rate of the over land. But of course, that's global. And when you look at it, when you break it down and look more spatially, these changes are not uniform. And we see that on the plot on the map on the left here, temperature, that there's a lot of global warming going on everywhere, but the trends are different. They vary spatially. In the middle, I'm showing the trend in integrated water vapor, and what that is just the amount of water vapor in the atmosphere. And you can see that there's been pretty substantial changes spatially there in terms of increases and some decreases in water vapor. And then these changes also involve and create precipitation, which again is spatially heterogeneous over the globe. And so the changes again are not uniform. Briefly, what makes atmospheric water vapor a major player in global warming is we have this kind of cycle that I've mapped out here. And as the atmosphere warms, the ability of the atmosphere to hold moisture increases. Also from the warming, we have increased evaporation, which stores heat through the process. Down here, the water vapor is a greenhouse gas, so it actually feeds back and increases warming and stimulates cloud formation. And finally, we have precipitation, which releases the heat that was stored by evaporation, and that increased energy increases storminess. And I think this is a lot of what we're seeing globally with these increasing intensity, big magnitude rainfall events. Some of this is being driven by this warming cycle that's going on. Not all of it, because certainly there's a lot of interannual variability that's just naturally internal to the climate system. But some of it definitely has been shown to be a factor. In terms of the events that occurred over the West and in the GYE in June, this slide shows the teleconnections that were in place in June. The top map is sea surface temperature anomalies relative to the climatology for June. And so what's pretty apparent here is that there's this big warm anomaly in the North Pacific, the classic El Nino or La Nina pattern here with increased cold water upwelling along the South American coast, and then propagation of that across the Equatorial Pacific. So this is the setup that we were looking at in June. The La Nina, this was the second year of the La Nina, and I think the forecasts now show a third year, and it's been since around 2000 that we've had 3 running years of a La Nina. Associated with that is the lower plot, which is the Pacific Decadal Oscillation. And you can see that through the spring and the summer of 2022, we're in a pretty negative phase of the PDO, pretty substantial strong phase, which is, of course, related to La Nina. And these events then were in place, and they have a variable effect on the GYE. Sometimes they follow the expected pattern, and sometimes they don't. So in terms of the patterns, and I think people are probably pretty familiar with this too. This is the March through May 2022 temperature ranks on the left and precipitation ranks on the right. And so you can see that there was a cool northwest in general, cool and somewhat wet, along with a dry, a warm and dry southwest, which is that's pretty much a standard pattern for La Nina. What this did, of course, was to delay snowmelt, actually allowed some snow to accumulate, and then brought wet conditions to the GYE with some quite wet conditions in Wyoming. So we have this La Nina in place, and cooler and wetter conditions that predated the June event. With the effect, of course, is that the snowpack was substantial and had not really started to melt out as normal. So atmospheric rivers, there's been a lot of research done on them, obviously, because they're big players, especially on the West Coast, California in particular, and Oregon, and just the Pacific Northwest and California are quite heavily influenced by atmospheric rivers. And just to give you an idea of atmospheric rivers, there's a scale that was put together by Marty Ralph and colleagues in trying to classify these. And right now, the scale, ranges from looking at integrated vapor transport, which is just the winds carrying the moisture along, and the duration of the event ranging from 24 to 72 hours. And the scale goes from not a river if the IVT is low, all the way up to exceptional when IVT is, the value of it is 1250 or more, and the duration is up to 48 or 72 hours. In terms of how these are looked at on the landscape, they've also done this categorization of on the right here of being beneficial, balance of hazardous and beneficial, and primarily hazardous. So for the June event, we were up here along the Pacific Northwest coast. We were up in this exceptional category in terms of the strength of it. And events this big are really pretty rare in the record. June events, atmospheric rivers, are just something that they do occur, of course, but they're pretty rare, and especially one of this magnitude. So what I did was I thought it'd be interesting to model this atmospheric river with our regional climate model, just to look at, diagnose it, and give you some idea of what they look like. I'm going to try to unshare my screen and share another one. Okay, so this is what I've done here is looked at integrated water vapor, which is simply all the water vapor in the atmosphere from the surface up to 300 millibars, which is roughly 30,000 feet. And that's basically the limit of atmospheric moisture. So I've created this video just to give you an idea of how this atmospheric river and the moisture related with it evolved through time. These are 6-hour time steps starting at on June 8th at 6 p.m. in the afternoon. And so I'm just going to step through this, and you can see the transition of the moisture streaming into the West Coast. And note also that this is following that, if you remember, that sea surface temperature anomaly, that warm anomaly. This is pretty much right along the edge of that. So warm ocean, lots of moisture, and it evolved into this AR. So as we go through this, we can see the time periods through the whole the whole event until we get over here in June, on June 12th at around 6 p.m. There's a lot of moisture now that's been pushed in to the GYE, and of course this is what triggered the whole rainfall event. So I took out a few snapshots of these conditions just to give you an idea further into what the conditions are. So what I'm showing here is this on the left is integrated water vapor, the video I just showed. This is actually integrated vapor transport that I was talking about. So it's a map of how much moisture and the direction of the moisture is being streamed in the AR. And then the precipitation that goes along with it. and then the lower atmosphere temperature. So on June 9th, this is when the AR was focused on, a very strong one on British Columbia, brought a lot of precipitation there. And note that over here, we've got a warming going on in the GYE around, or actually in this region in general. The lower map on June 11th, or the lower strip of maps, the AR has moved southward. It's focused on Oregon, and you can see through the vectors that it transports right into Oregon and Washington. And this is what caused a lot of precipitation to occur in Oregon and Washington. I think, I can't remember for sure, but I think we had nearly an inch of precipitation in Corvallis. And then note also that there's increased warming going on here in the GYE. And this is what started the snow melt before the AR actually hit. This is what started snow melting in the area. Now to the conditions that existed when the precip actually happened in the event on the 12th and 13th. You can see that there's a lot of moisture in the atmosphere here on the 12th. There's still a fair amount of transport going on, and this is the beginning of the heavy rainfall event that occurred under warm conditions that existed at that time. And by June 13th, the moisture had started to exit the area. There's still some around, but because local circulation changed, the moisture's exiting. We get the last burst of precipitation, and it starts to cool off again. So, you know, in terms of our modeling, it pretty much explains what was going on with the dynamics at the time. I think the model does a pretty good job of capturing this, and it's pretty. I found it pretty interesting to look at the dynamics. Okay, as far as ARs in the future, you know, the idea that the atmosphere is warmer, it can hold more, there's greater moisture capacity, implies that there will be more intense ARs. And some of the research that's out there, modeling research out there, shows indeed that there's more intensity to them just from that factor. Some studies indicate that they will be slightly more frequent, some less, and some not much change. So the frequency and the ability to model the frequency and look at significant changes in the future is somewhat limited. It does appear that there will be, because the gradient between the temperature gradient between the poles and the equator is relaxing as global warming goes on, there's going to be an equatorial latitudinal shift. And some research also shows greater inland extent. So places like the GYE, the potential exists for the extent to, for them to be more frequent or penetrate further, although that's not a certainty. So finally with the ARs, when you see an AR on a radar map, you know what it is, or if you look at the simulation I just showed, you can tell what an AR is. But to look at them in the past or in the future, we need to rely on models. And it's actually a pretty difficult problem to come up with a way to automate tracking ARs. And this is just an example of a study that a colleague of mine at NCAR ran, where they compared a number of different tracking methods to see how they compare in terms of being able to identify ARs in climate model simulations. This was done basically on observed data, but the goal is to be able to do this with models. And I think there were 15 participating groups in this. And I've just shown you here that there's all kinds of things that need to be addressed in these, from the geometric requirements. You know, they have to be a certain length long. There has to be a certain threshold value for integrated vapor transport as it arrives on the coast. And there has to be some kind of temporal requirement as well, if you remember the chart. So, looking at this in the future, the good thing is climate models actually do produce ARs. The real challenge, though, is being able to sift those out and make some kind of statistical statement about the where, when, and how frequent. So let's shift now to looking at some of the work we did in the GYE that's related to this. These are taken from our climate assessment, and what I'm showing here is the observations show that since 1950, below 8,000 feet, the mean temperature has gone up about 2 degrees, 2.3 degrees. So the warming since 1950 has been pretty substantial above 8,000, below 8,000 feet. The mean annual snowfall over that period snowfall has decreased by 24 inches. This is limited to 8,000 feet and below because we simply don't have the weather stations at higher elevations. So we have some idea about what's going on with snowtel sites at higher elevations, but that data for the assessment sometimes they're very difficult to put together in a uniform way. So we relied on the meteorological stations where we have those observations, and they're pretty well documented. So warming and less snowfall. And it looks like in terms of at least the AR5 assessment in terms of representative concentration pathways, that warming through the 1900s, 1950s, and so forth is related to, is related to the CO2 atmospheric SOT levels. And what I'm showing here are the RCPs that were considered for the last IPCC assessment. And the two that we looked at in the GYE assessment is the RCP 8.5, which is basically a business as usual or without much mitigation in terms of carbon dioxide and greenhouse gas emissions. And then RCP 4.5, which there is mitigation mid-century, and that ends up capping the temperature rise associated with greenhouse gases. So this is this is a plot of the GYE annual temperature departures from our assessment, and what I'm showing here in black is the PRISM data. So these are observations over the period of record through about 2005. So this is the variability in temperature over the GYE in the observations. The red line is the RCP 8.5 scenario, temperatures associated with it. The heavy red line is the median temperature for 20 climate models. And the envelope is the 10th and 90th percentile spread in those models. The blue line, go back. The blue line is RCP 4.5. So the one with the RCP that there's a mitigation mid-century and kind of caps the rise of temperature. And by the end of the century, it's about a 5-degree difference between the two. One thing that I find interesting in this is that if you look at the spike in the 1930s in the observations and run that out in time, somewhere around in the 2030s, the median models are showing that we've reached that level of warming, and there's probably no return on that if you follow either of these RCPs. So it becomes pretty apparent that climate variability that's been extreme in the GYA over time could become more or less the average. Another way to look at this, look at these changes, which sometimes makes it a little more, a little clearer, is to look at the distributions. And so what I'm showing here on these plots are the top on the right here, or left here, are maximum temperature. So maximum winter average temperature, maximum spring average temperature for the historical in blue and RCP 4.5 in red. And what these show, the dashed lines are the averages or the median for the models for that period. So you can see that there's a pretty big shift in the distribution of temperature over the winter average, with a substantial shift to the warmer part, a substantial warmer shift occurring in the winter, another shift occurring in spring, and in minimum temperature, which I'm showing here in the bottom, there's even a bigger shift. So the temperatures both in winter and spring are shifting warmer, and you can see that the interesting thing here is even under RCP 4.5, what was in the tails of the distribution for the observations now becomes the mean or median for the shifted climate. So again, these illustrate how we're moving into new territory, or potentially could move into new territory. In terms of precipitation on the left, this is winter, spring, summer, and fall. There's not a lot of shift in precipitation. There's some in terms of spreading out the distribution. In winter, for instance, decreases the peak and spreads a little bit more into higher precip values. But overall, the precipitation distribution, we don't find much difference in both the projections from the observations. So basically, we're looking at a warmer, potentially somewhat wetter, but not a lot wetter situation. So what does this have to do with the snow? This figure shows how through time the distribution, the elevational distribution of rain and snow might change in the GYE. The top row of maps shows the blue is where currently snow dominates the precipitation, the winter's precipitation. The orange and the red are transition areas where snow and rain are mixed, and the blue areas, or green area, I'm sorry, is straight up rain. And so as we go through these periods from left to right, so this is the control on the far left, or present day, you can see the shrinking areas of these various components of precip. And by the time we get to the end of the century, only the highest elevations are actually snow dominant, and a lot of it's been replaced by the rain snow mixed, which is the areas that are currently and in the future will be most susceptible to rain on snow type events, because those are the areas that are most prone to have substantial changes in temperature, warm fronts coming in and occurring and causing these events. On the lower panel, this is just through time on the time axis, the elevational shifts in these zones, and the up and downs in these bars are actually interannual variability that's simulated by the model. But the main point here is that by 2040, this zone, the mixed zone, has increased a lot in terms of elevational coverage, and we hit 8,000 feet, and now it's clear up into and above 8,000 feet in terms of that precipitation form being a rain-snow mixed. And how this plays out in terms of runoff climatologically in the GYA. This figure shows where the runoff through time, where the runoff is generated. So the bottom is the months, a monthly calendar, and elevation is plotted on the y-axis, and you can see that a lot of the runoff that occurs in May, June, July is coming from, the 8,000 to 9,000 foot region. And here we've plotted up the limit of the transition zone and the limit of the snow dominant zone. So above this is snow dominant. As we go through time, through these periods in the future, what you can see is that there's a shift starting to take place, less runoff happening in May, June, and July, more in the early spring and winter, as these transition zones, the elevation increases in both the zones. And by out here towards the end of the century, by the end of the century, there's a substantial shift, and you can see that, we've lost all this runoff that's occurring at around 8,000 feet in the summer, and it's now occurring in the winter and early spring because we've shifted the transition from snow to rain. So one thing that I didn't have forecasts of ARs, but one thing we can look at is projected changes in rain on snow. This is a climate modeling study done by Musselman et al., where they used a really high resolution regional climate model and looked at changes in potential rain on snow events throughout the West, and including the GYE. And so I use this as an example of to look at how things might change with rain on snow events. On the left here, we have rainfall intensity, the difference in rainfall intensity at the end of the century versus basically present under RCP 8.5. And what this shows is there is some, over the GYE, there is a mixture of changes. Some intensity is shown to be going down, some intensity has been shown to going up. On the right is the percent of snowmelt contribution to runoff. So in the GYE, it's a very mixed signal. There's more coming from the high elevations, as I showed, less coming from the lower elevations as we transition out of the snow and rain, the current snow and rain situation. So also in this study, they did a really nice summary of the potential changes in flood potential. And this is, they scored the top 10 events in magnitude in the West and looked at the statistics of those. And on the left is the change in days per year that these flood generating events might happen. And you can see that the GYE in general has a slight increase of 1 day or maybe 2 days at most. But again, as we know from the event this year, it only takes 1 or 2 days. So an additional 1 or 2 days of those kinds of events could possibly be a pretty substantial change in the rain on snow and flood events in the future. In terms of volume of water generated, in the GYE, we have a mixture, but mostly the volume of water is projected to go up somewhat. The spatial extent is expected to go up somewhat, and the intensity of flooding is basically in the GYE, most of the GYE not shown to go up substantially. So more extent, more water, but maybe no increase in the intensity. And this is a modeling study, so it does have it does have some limitations, but I think it's a good example of what we might be able to expect in the future, or at least it's an indication of the direction things might go. And I think with that, yeah, I think with that, I'll end the presentation and take questions if there are any. Thank you.
Thank you, Steve, for such an interesting talk. It also makes me really worried for future ski seasons. I'd like to invite the audience to unmute yourselves and ask questions.
So Steve, maybe I could ask the first question. Again, thanks for that. Really fascinating, particularly nicely summarizing the future projections for average conditions, but also really raising the question about change in extreme events. It seems like in the last 10 years, nationally and globally, we've seen the extreme events wreaking havoc in many locations and having huge impact on people and on policy. And I just wonder, your talk makes me wonder whether we could identify the types of likely extreme events, the types of extreme events that may increase in likelihood in GYE, and who they might impact, and what the costs might be, and how they might be mitigated. So more specifically, you mentioned the atmospheric river phenomenon, which seem to have big consequences for snowmelt and flooding. And of course, another type of extreme event is drought, perhaps upland drought that affects upland crop production, or drought that affects runoff and irrigation and water supplies to cities. And then severe fire as an extreme event, and then perhaps, extreme avalanche cycles or landsliding. I'm just wondering, can we move towards identifying the types of extreme events that might be gaining in probability here and beginning to assess how important they would be to us, what some of their consequences would be, who they would affect? I assume that each of these types of extreme effects influences different types of stakeholders in different places. It's almost like shifting from observing extreme effects to predicting them and anticipating their consequences and trying to be prepared for it. Sorry for the open-ended question.
Yeah, that's a good one. I think we have the observational record, we have the paleo record that we can look at to see what's happened in the past. So that's what we know. In terms of projections, these types of things are difficult to project. In a small spatial area, mainly because of limitations. We have to rely on models, and the climate models are somewhat limited in being able to do that. And again, we have a fairly wide spread in models. But to answer the question in general, I do think we've made progress, and I do think we can make more progress as time goes on with our modeling abilities. Because again, we have to rely on the models, and one of the thing that's always difficult with the models is the uncertainty. As I showed that one plot of temperature, there's a pretty wide spread in model uncertainty as you get out further in the century. And so that complicates a little bit when we're looking at extreme events, which are themselves, out on the tails of the probability distributions. It gets a little bit confused, but I think there are general things that are going on that can be related to, for instance, drought. We know it's warmer. It's been warming. It's going to get warmer. We know there's shifts in stream flow. We know that the annual cycle of aridity is going to probably deepen a bit in the Yellowstone area. So we do know those things, but I think actually forecasting specifically the magnitude and distribution of those events is still pretty challenging.
Good, thanks.
Go ahead, Zach.
Hey, Steve, do you have a sense of the snowmelt's contribution to the runoff and the eventual river discharge from June?
I'm sorry.
Oh, sorry. Do you have a? Can you hear me now?
Yeah,
Any
I
better?
can now. Yeah, sure.
Okay.
Sorry.
Do you have a sense of the snowmelt's contribution to the runoff and eventual stream discharge from the June event?
I didn't do that calculation. I think there are. I'm trying to remember. I think I read somewhere a summary of that I could probably try to send you. There was a summary done at the Weather Service, I think, and I think NOAA was involved in that. And I'm trying to remember. I think there was a pretty substantial snowmelt contribution on top of the rain and the rain on snow event. So I think the snow melt had started before the event actually occurred. And that was a fairly substantial, abrupt increase in snow-generated runoff because it warmed so much before the event. But I don't have the exact number.
Yeah, I'm working on a master's thesis at University of Montana, looking at geomorphic change from the floods in Yellowstone.
Yeah.
This June.
Yeah, right. Well, you have a lot to work with there.
Yeah, I know.
Yeah, I could try to look that up. I read that a while back, but I don't remember actually.
Okay.
So Zach, keep us posted on your findings. That'll be of high interest to a lot of us here.
Oh yeah.
Yeah. Yep. I'm sure you'll see it out and about at especially at University of or at Montana State presentation. Yellowstone.
I have a question.
Sure.
Yeah, Dave here, Dave Klumpar. I'm not a hydrologist or I don't work in this area. But what strikes me, my curiosity, the root of my question is you mentioned a few minutes ago the paleo record. And so I'm curious to know how these projections compare to what we know about, previous millennia and global periods of global warming and the consequences that we know about, by looking at the geological records on shorelines and so on. How do these compare with what we know in the past? I mean, are we approaching just is there any way to quantify it and just to compare with previous episodes of global warming?
In the GYA. So this period is obviously very warm. And we haven't seen a lot of it, at least in the paleo record that we can see, that's been warmer than now. we do have records like Kathy Whitlock's lake records, et cetera, that we can look to see how that affected vegetation, wildfire, and hydrology. And there's been some work done by some people who looked at the cessation of Old Faithful back in the mega droughts in the 1200s. So we have records that we've been able to piece together to know that in the past the GYEs experienced pretty substantial climatic and ecological change coupled together. There also is some indication, Brian Schumann down in Wyoming thinks they have some indication of AR activity making it inland into some of their lakes in Wyoming. So one of the things I want to look at when I eventually get the Holocene record to a point I think is worth comparing to see if we can actually start to look at events, but those events are pretty difficult to pin down. But yes, the paleo record is the thing to compare with and compare to, and as I said, we see this as a very warm period right now.
Interesting. Thank you very much.
Sure. Thanks for the question.
Andy, I think you're muted.
Yeah, thanks. How has the Montana climate assessment been received? What sort of types of applications have you learned about, or what types of responses have you got from different communities in our area?
We've had quite good response. Unfortunately, the assessment came out with the pandemic going on, so it kind of limited things. But the Greater Yellowstone Coalition's done quite a bit of work with it in working with interested groups in the region. We've given a number of presentations to different groups. I think that we're just starting now, I think, to be able to go to break this down to smaller meetings, and we hope to do some localized meetings where we can actually engage stakeholders and people who are interested in climate change in the GYE.
You know, once again, I'm really struck at how the demand for climate-related science is changing rapidly. How, you know, as recently as 5 or 8 years ago, kind of the state of the science was to do projections out to 2100 under scenarios through the GCMs and looking at mean and variability. And I know in my own experience, the many resource managers found that interesting, but really not something that impacted them, what they were doing that day or that week. It wasn't front burner, of course. They had many other issues that were more front and center. And so while that science was interesting, it just wasn't that relevant in the eyes of many land managers to their immediate decision making. And since then, these extreme events have, I think, totally rearranged that, where now the challenge is, how are we going to cope with the fires during this, you know, this fire season? How would a fire manager distribute resources across their area to try to accommodate the level of firefighting needs that are likely to be required and to protect homes? And then how do we anticipate what roads might wash out in the next atmospheric river event? Bug kill, how to manage forests to reduce fuel loads. It seems like the managers now are really demanding science on how to cope with these extreme events that are becoming more typical. And I just wonder what you think about the ways that we scientists can respond to that and begin to help answer some of those near-term questions of actually coping with, you know, these weather changes, if you will, these extreme weather changes.
Yeah, it's a good question, and you pointed out one of the challenges always when you're in climate research like we are is bridging the gap across to people who could use the information and how they would use it and what questions they would ask. But in terms of the end of what you were talking about there, I think these extreme, I agree 100%. Extreme events get people's attention. And now that we know that this kind of event, like happened in June, happened and could occur again, then you can start to look at things like the road building. What were those roads built? What kind of flood return period were those roads built for? Was that even considered? Wildfire, the same deal. Here in Oregon, we have one really big fire this year, and of course, a couple of years we had devastating fires. And the setup for these fires in Western Oregon, anyway, is that the fire gets started somehow. We have a wind event, then it's like a blowtorch going down the canyons. In that case, they were started like in California and other places by power lines going down. So this fire that's going on now up west of us here or east of us here, they simply cut the power off to the entire region to prevent additional lines coming down and additional fires to be started. So those are a couple things I think that are reality based, and I think they're things that managers of whatever utilities or road building or firefighting can look at and try to act on or plan for. And if we just can make, if we can just say that in the future, if we know in the future that these events will be more frequent, maybe higher magnitude, then that gives a background for motivating changes that need to be done.
Any final questions? Paige, we're probably running out towards the end of the hour. Well, maybe I could just reiterate Paige's opening, how much we appreciate Steve taking time and sharing with us, this really fascinating information. I just love that video of what actually was going on. It really helps us, visualize and understand the sort of processes you're talking about. Looks like one question, Jeff.
Hey, thanks, Andrew. Steve, thanks for the presentation. I live here right on the Yellowstone, 10 feet from it, just north of Yellowstone Park. And so, was excited to see your presentation and many others from the state, especially the state hydrologist. I was keyed in on one small comment you made in your presentation about, and this goes back to Andrew's point of how does a local community process this data? Well, they tend to process it by saying, what's the impact to you? How do you predict the likelihood of a flood event or a fire event and those sorts of things for agriculture, for business and whatnot? We all know, like Gardner, for example, is down 80% in terms of economic output this summer. So the impacts are big, but helping take the science and translate it into a little more nuggets. So one thing you said was really tipped me off was there's a lot of debate around here is what's the likelihood of this type of flood event happening again? And you mentioned that small variability of, I think it was one possible day a year increase based on the model. Of course, that depends on how you define 1,000-year, 500-year event. Can you like pull some layers off of that onion and kind of maybe explain why you're hesitant to, or what we need to know, or how we quantify what is the increased likelihood over time of that AR on a not dense snowpack like we had this year that resulted in that extreme flood? I don't know if you know which slide I'm talking about. I'm not doing a good job, but it was the increase in number of days a year you would have this similar AR.
Right. Well, I think there are a couple things. The reason I hesitate is this is a model-based projection, first of all. So for the situation that you described, we'd have to be able to model first the AR, the precip event, and then the snowpack situation that contributed to it. So that's a pretty big challenge when you're trying to do any kind of modeling of that event. And I think, any of the hydrologists that worked on this or looking at this will tell you the same thing, is that it's a pretty difficult target. In terms of, maybe one way you could go about this would be what's done commonly with the IPCC is to look at, have a suite of high resolution regional climate models that you would all simulate the future and look at the ARs in there and get some kind of distribution among those different models that would give you a little more confidence in if there's higher intensity, more frequency, whatever. But, I think the point also is that, if you increase the likelihood by a day or two, we saw this year what a day or two can do. So, I mean, that's pretty substantial. It's not as though that event wouldn't have an impact on the area. But again, it's a pretty difficult target, I think.
Thank you. And thank you, Andrew, for your point earlier.
Okay, well, great. I hope you all will join us next week. Arthur Middleton will be fascinating. He's led ungulate migration studies around GYE. He was very instrumental in that National Geographic year focusing on Greater Yellowstone and the products that came from that. And right now he's very involved with the Biden administration's America the Beautiful and 30 by 30 initiative as it's being applied to GYE. So he will be, I think, really informative for us regarding science and policy across this large wildland landscape. So again, thanks so much, Steve, and hope to see the rest of you.
Thank you.
Next week.